Okay, so welcome everybody, and thank you very much for attending this workshop. The objective bueno, I'm Miguel Martínez Iturralde. I'm from SAID, from this research center. I'm the coordinator of the Addimot project. The objective of this workshop is not only to present the results of Addimot project, which we will present, but also to talk about the possibility of using additive manufacturing for the production of electric motor components in the future, in the near future, we hope. Okay. We are attending here in person, but also we have a lot of people connected. We are about 40 people attending this workshop. Please, the people who are online, ask your questions by the chat, okay? And I will read them, and then I will do the questions to the presenter, okay? We're going to begin with a very brief presentation of the partners that have taken part in this project, which are Safran Electronics and Defense, Egile Mechanics, and SAID. So I give the floor to Blaise Lapote from Safran Electronics and Defense. He's going to present his company. Thank you, Blaise.
No. Hello, I'm Blaise Lapote from Safran Electronic and Defense. I will present Safran Group and Safran Electronic and Defense, one of Society of Safran Group, very quickly. We are in aerospace. We are an aerospace company in France. The company have the possibility to have a social reason, and for Safran, the social reason is to have a more suitable aeronautic and world safer place is the two main objective of Safran. I don't know okay. I don't know okay. Safran, in terms of group, it's 78,000 employer. We have 15 billion of revenue. It's a old company, and we are third in the world in terms of size of a company. No, who to? Okay. In terms of in the world, we are present everywhere, but particularly in France, where they have half percent of employee, and we are in Europe, Asia, Africa, and America. We are everywhere in the world. Maybe it doesn't work. In terms of research, Safran spend 10% of revenue approximately, and in this R&D part, 75% are for environmental impact of aircraft, and they have 12,000 people approximately work only on R&D in Safran. Yes. We are present in all aspects of aeronautics, in propulsion with particularly in landing system, and for today more interesting is electrical electrical system, but we have also activity in space, in particularly for propulsion of satellite on space optic, and in defense, in particular in navigation and guidance and optronics. It's the two big specialty of Safran. Inside of Safran, we have a different society. We are in Safran Electronic and Defense. It's 9,000 employees. We are different specialty inside of Safran Electronics and Defense. Electronics and defense, of course. 50% of activity are for military project and 50% for civil aircraft, in particular for all electronics in aircraft, but also for the actuator. And me, I'm work on the service for the actuator. In terms of actuator, we produce different kind of actuator. They have some actuator for the cabin, for the seat, in particular for the business seats inside of aircraft. You have also ETRAS is for brake the aircraft with a thrust reverser. You have a secondary flight control. Can you see here? For example, the horizontal HSTA, it's horizontal then. Also, we have some actuator for the primary control that it's more prototype for the moment. It's not a reality inside of aircraft. And after we have many actuator inside of cockpit, in particularly throttles, but also state unit. What we will go to speak today and the application we have chosen for the Addimot project. But we have also actuator for all aeronef type like helicopter, VTOL, or regional aviation. Just yes, and today we will go to speak about SSU actuator. Maybe I stop here. I speak after of Addimot project for this part.
Okay, thank you everyone for coming to this workshop. I'm Ekain, head of R&D at Aguile Mechanics, and I'm going to present you very briefly our company. Okay. This one, please. Okay, we are an industrial and technological group which provide special services and products in the field of high precision mechanics. We are located in the north of Spain, between San Sebastian and Bilbao. Just some numbers of the company. We have more than 30 years of experience in the field of mechanical components, and there have been more than 7 startups that have been born from Aguile Mechanics R&D projects. We have a revenue in 2021 of almost 24 millions, and we invest about the 11% on R&D projects. We are almost 200 people, and just as curiosity, Aguile in the local language in Basque means maker or who makes. We are divided in 4 different divisions. 2 of them are related to the aeronautical sector. The first one is Aguile Aerotransmission System, which is a manufacturer of different components for airplanes and helicopters. Also, in the aeronautical sector, it is Aguile Aero Engines, which is specialized in the manufacturing of different components for airplane engines. But also we have another division which is focused in the manufacturing or providing the whole system for the manufacturing of cans for the industry of food and beverage. And there is another fourth one, which is Gila Extreme Precision, which is the most advanced division in terms of manufacturing precision. They usually work for those big scientific facilities like CERN. This one, please. Okay, sorry. This one. Just a little bit of history. As I told, we started 30 years ago manufacturing components for the SPPS project. We started with small batches, spare parts and prototype. And over the years, we take the access to new platform and new systems. So currently we are manufacturers of many components that are involved in many mainly Safran helicopter engines, but also we also work for Airbus and other big players of the industry. Currently, we are working in the diversification, in internationalization, and the vertical integration of the processes that are needed for the manufacturing of our products. Okay. Here are some examples of the components that we manufacture for the helicopter industry. For example, we manufacture auxiliary and power gears for the main gearbox and auxiliary power gearboxes. Also tail rotor components, transmission shaft, and we also provide the whole system, such as oil pumps for the lubrication of the main gearbox. Just some photographs of some of the components that we have in serial production: auxiliary gears, power gears, housings for the gearboxes or shaft. The division of Gila Aerosystem is focused in the manufacturing of different components for the landing gear of the airplanes. We provide this kind of kitchens, which are the parts for the assembly of the shock absorbers, retraction actuators, and all the components that are needed for the assembly of the landing gear. As you see, we are involved in many programs for the airplanes from Airbus and Boeing. And here just some examples of those boxes that we provide with all the components for the landing gear. Okay, the division of Gila Aero Engines is focused in the manufacturing of NGVs, nacelle guide vanes, and airfoils. However, we also have some projects where we manufacture other components of the engines, such as main shaft, transmission components, lubrication system components, and so on. So also in this area, our parts are located in many plane and helicopter programs. As I told, one of the lines that we are focusing right now is the vertical integration in order to be able to provide our components with the whole system done in-house. So we already have the NAPCA certification for carburizing and night treating, and for sure also for other heat treatments such as quenching, tempering, and so on. And in order to provide the whole process in-house, we also have integrated those special quality processes that are needed for the certification of the quality of the components, such as magnetic particle inspection, liquid penetrant testing, Barhausen noise, and so on. In order to do so, we have a new facility in Itziar, where there are more than 6,000 meters squares of open workshop. And here some examples of, sorry. Okay, here we are. This is an example of our facilities in Itziar, the new ones, where you can see the furnaces for carburizing and night treating. Also the line for the washing of the parts before and after the heat treatment, the laboratory. Here just some of our customers of the aeronautical sector. Our main customer is the Safran Group companies, which represent about 40% of the revenue if we take into account just the aeronautical sector. And if we consider the whole Egile Mechanics, it represents more or less the 20% of the revenue. But we also work with other big players of the sector, such as Airbus, Avio, Eurotech, ITP, and so on. And okay, that was regarding the history of Egile Mechanics and our core, which is the manufacturing, but we also are able to provide integral solutions. In terms, we are able to work taking from a load book, make the preliminary and detailed design, for sure also the manufacturing, the assembly and testing of different components. We have 4 development lines. However, they are closely interrelated in order to provide these complete solutions. The first one are the transmissions, which is the historical product of Egile Mechanics, but also we are working in oil and fuel pumps, electrical motors, and metal additive manufacturing. And okay, just to finish some slices with finished projects. This is an example of a Clean Sky 2 project that we performed with the collaboration of Safran helicopter engines and Safran transmission system, where we co-designed with them the gearbox of the TEC-TP project. And we also manufacture the components and the assembly, and they have been testing in the facilities in Internos. Here another example, also for Safran, where we designed a very high speed double epicyclic gearbox. Okay, we did the calculation, design, the assembly, and they have been testing in 2021. Another example, this case, this is a Wolfram gearbox for the space sector. The peculiarity of this gearbox is that it has a very high reduction ratio of more than 200 and anti-backlash system in order to avoid any undesired movement of the output. I think that it is also a good example because we also introduced the metal additive manufacturing in order to achieve the specification of the client. And sorry, as I told, we also are providing different solutions for the lubrication of the airplanes. We are designers of gear rotors and gear pumps. It is another example where the additive manufacturing might introduce some benefits, at least in this moment for some prototypes that we have been performing during this year. And that's all. Now I'm going to let my colleagues to start with the aim of this workshop, which is the Addimot project. That was a Clean Sky 2 project with Safran as topic leader, and we worked with Fate in the development of this electrical motor. So thank you. If you have any question, please contact me. Here you have my email, or as you wish.
Thank you very much again. Now I'm going to do a very, very brief presentation about Fate for those who don't know us. Let's see. Yes, Fate was founded 40 years ago. Just this year we have the 40 years celebration from the School of Engineering of the University of Navarra. We are a research and technology center. Okay, and that's our mission is developing research projects with industry, training young researchers, and also the dissemination of knowledge. We are a non-for-profit institution, so all the benefits are reinvested in research. okay? As we have this mission, yeah. We are very active in scientific production. We develop PhD thesis with young researchers, okay? And we also, as we do some research, okay, we normally do some research for industry, but also we do some research our own. So there's sometimes that we reach a TRL level sufficient to go to, let's say, the market, and thus we create some spin-offs from Fate, okay, and now we have more than 300 employees in spin-offs created from this in this scheme, okay. We are more than 200 people with a great amount of doctors. We have a huge scientific production. Our income last year was 19 million euros, and the share of the budget, let's say, I think that says a lot of our about our activity. Okay, we have, as you can see, 41% of the budget directly with contracts with industry. So it is research, but it is innovation development, let's say, very applied research. But we have base funding from the Basque government based on some indicators as patents on publications, peer-reviewed publications, and PhD thesis, and so on. And the other 40% is based on, let's say, public competitive funding. As for example, the Addimot project. The Addimot project is a European project. It's funded by the European Union. And this kind of projects, we use them for creating new knowledge, let's say, with the objective of transferring it to the companies, to the other 41%, the blue part of the cake. Okay. So we have very applied research with industry. We have some, let's say, more basic research with competitive funding, and the thing is to balance both, okay, so that with the, let's say, the orange part, we can create new knowledge to later transfer it to the blue one. Yeah, we have 4 divisions in Fate, 3 vertical divisions. It's materials and manufacturing, transport and energy, and water and health. And we have a 4th division, which is more transversal to give that gives service to the other ones about information and communication technologies. Okay. We are very active in thermomechanical processing, advanced powder metallurgy. We will talk later about this because it's very related to the Addimot project. Mechanical design and assessment, and also industry 4.0. Okay. In transport and energy, very active also in the railway sector, okay, electric vehicle sector, and in the aeronautics sector, as we don't have a specific group with the name of aeronautics, but in transport and energy, we are very active. And also water and health in the water and waste treatment, okay. And the division of information and communication technologies, we have several, let's say, basic groups that give services to the other divisions. And finally, talking about the aeronautics sector, we are very active in the last years in several, let's say, activities, and modeling and characterization of materials and manufacturing processes with a huge experience of nearly the 40 years of the center with some clients. Metal powder and laser based manufacturing. Here the activities are related to powder production and also additive manufacturing, very related with the Addimot project. Industry 4.0 for aeronautics, also with several clients, and also the design of electrical machines and power electronics for more electric aircraft. Okay, the joint work between the second point and the 4th point has led to a project like Addimot. And finally, just some clients that we have in this sector. We work with major actors, it's ITP Aero, Airbus, Leonardo, and also with Safran and other clients that we work in this sector, of course, with our colleagues of Aguile Mechanics. Okay. And that's my brief presentation of SAIT and our work in the aeronautics sector. Okay. Now I'm giving the floor again to Blaise, just to give us the context and the objectives of this Addimot project. And now we begin with the technical session. Okay. Blaise, please.
Which one is for?
It works sometimes.
Okay. Okay, let's go. I will present you the challenge of Addimot project. For start, I will speak about the application use and the use case of the motor we will speak today. It's an active inspector, like you see in here. This inspector for Safran, it's active system, and the objective is to have the possibility to have an evolution of the law during the different phase of a plan, and the possibility to change the law in function of what you want to do with the aircraft and etc. And the capacity of this inspector, you have a virtual stop, and for that you need a very hard and very high level of torque in the motor, and also the capacity of simulate the link between the pilot and the co-pilot to have more information and not verbal information between the two pilots, because today in Airbus, for example, you have no link, and the pilot and co-pilots have no the information what do the other. Safran wants a very big quality of ergonomic for the ergonomic aspect, and for that we have choose to have a direct link between the end of a pilot and the motor, because if you have a reduction, you have a low ergonomic sensation. But the problem when you do that, the motor is very big, and you need a very high level of torque inside of the motor, and that is the main problems. It's for that we have choose to this motor for the Addimot project. If I make a focus on the motor, the functional envelope, it's 100 by 100 by 100 millimeters. If it's smaller, it's better, but it's what's the place we have for the moment. The level of torque, it's around the 10 Newton meters. And it never do one turn, just 70 by 70 degrees. The most important things for this motor also, it's the quality of the torque, because you have a sensation, and the sensor of the human, the hand is very sensitive, and for this reason we want to have no cogging torque in this motor, or very small. The ripples need to be to be minimized, and the friction also need to be very small. Also, the last aspect is the consummation, because you are in an aircraft, and the level of consummation need to be very low. You imagine the torque have no movement for a grand part, and they have no power. You have only loose inside of this motor. Okay, the main goal, it's a very classic: size, weight, and cost compared to the traditional technology. What's the additive manufacturing capacity in this in this subject. And in particular, for the question for Safran, it's who is possible to do with a new degree of freedom of additive manufacturing in terms of topology to meet the need of the motor in terms of quality of torque and size also. The second point is what is possible to win in terms of weight, because it's the first aspect inside of this technology. The third one is which material we will go to print. Okay, magnet or not, copper or not, for example, or only ferromagnetic material on mechanical also, because they have some mechanical parts inside of the motor. And for Safran, one of the big points is to have a final prototype and functional prototype. And that is very important to be sure, because sometimes we have many bricks of technology, but you have no final products. And when you integrate all the time, you have some problems. And the last aspect is the cost, because if the cost is it's too heavy compared to the traditional technology, it's also a problem, because the first objective of the company is to make money, of course. Okay, I think I finished about the goal and the objective of Addimot project. Maybe they have some question on this application. And well,
Okay, thank you very much, Bless, for giving us the context and the objectives of Addimot project. So it is the use of additive manufacturing for electric motor components. So we're going to begin by the beginning with the production of the powder needed, the raw material for magnetic and structural components. José Manuel Martín and Miren Aristizabal are going to introduce us this aspect, not only the Addimot results, but also an overview about magnetic materials for additive manufacturing.
Well, good morning, everyone. My name is José Manuel Martín García, and I will do this presentation with Miren Aristizabal, my colleague. Just I will do a general introduction about additive manufacturing of magnetic materials, and in particular, the process of selection of the materials for this project. And later, Miren will present the technical results in more detail. Yes. Sorry. Well, this is the index that I will follow during presentation, and just I will focus in these two initial points. So first, we belong to the materials department, and our activity in this project has focused on the selection and developing of the materials. And in particular, the problems in this project were related with magnetic materials. In the case of magnetic materials, what is the characteristic behavior of this material is that when we apply an external magnetic field, H, they respond generating a strong internal magnetic field, which is the magnetization, which amplify and add to this external field. The material response is characterized by this kind of curve, which is in a hysteresis loop. And depending on the shape, depending on the shape of this loop, we talk about two different kinds of materials: hard magnetic materials. We have a wide curve, and soft magnetic materials. We have a narrow curve. Both kind of materials are relevant in the design and operation of electric motors. First, as I mentioned before, the characteristics of hard magnetic materials is that they have a very broad hysteresis loop. Typically, in operation, what matters is the second quadrant of this hysteresis loop, and in particular, what is called the demagnetization curve. The application and the shape of the magnets define what is called the load line, which is this straight line here, and the intersection of this curve, the demagnetization curve, with the load line determine the operation point P. The motor or the device and the magnets must be designed so that this point is as close as possible to the point where the magnets are able to deliver the maximum energy, what is the maximum energy product of the system. Two other important properties of hard magnetic materials are the coercivity, which is this point here, the maximum H file that the material is able to withstand in operation. And secondly, is the remanent, which is the B file here at this point, which is related with the maximum torque that you can deliver that the motor can deliver. In the case of the soft magnetic materials, the main characteristic that they must exhibit in application is that they are easy to magnetize and demagnetize, consuming very low energy. In order to do so, as mentioned before, the curve must be very narrow. That means that they must have a very low coercivity. If possible, the permeability must be as high as possible, because this is related with the velocity at which the material can respond during magnetization, demagnetization. And finally, another important property is the saturation magnetization, or the saturation magnetic induction field, which is an indication of the amplifying power of the external field that you are applying in operation. I don't know what is going on with this. Sorry, you can. Yes. The materials are going to be processed by selective laser melting in this project. And the characteristics of the powders used in this additive manufacturing technology basically are that they must be spherical to have a good flowability and form bed with uniform density. The particle size distribution typically, typical range is between 20 and 63 microns. And they must be, as well if possible, with a low oxygen content. So gas atomization is a very suitable process to produce this kind of powders. Sorry. In CIT, we have two facilities to produce gas atomized powder. The first one is a small atomizer of large scale, where we are able to produce 3 kilograms of powder per experiment. And we have as well a big atomizer where we can produce 200 kilograms of powder per experiment. In the process, basically, what we do is to charge the raw materials in a induction melting furnace. Here we melt the materials and they get alloyed, the different alloying elements. When the melt is homogeneous, we lift up this rod, which is called the stopper rod, and the metal is driven into the atomization chamber. When the metal arrives at the atomization chamber, we turn on a supersonic gas flow, we impinge with this metal flow and break into particles. In that way is how we produce the powder. Later, the powder can be mixed with other additives, so we have mixers, or can be sieved to separate the side fraction of interest, like for example in this project. And finally, the powder is packed to transfer to further processing. In this project, we have considered the use of 1 hard magnetic materials and 3 different soft magnetic materials that you can see in the slide. Regarding the hard magnetic materials, the the material of choice was the neodymium iron boron. We are able to atomize this material to produce, but finally it was discarded to process this material by additive manufacturing. There are two reasons for that. The first one, well, this is the microstructure of the material of the powder. If you process by additive manufacturing, you are going to melt this powder and you are going to solidify. So the microstructure is going to be different to this, but it's going to exhibit some main characteristics that are going to be equivalent. The first point is, as you see here, there is always some residual alpha iron, which is a soft magnetic phase. And this, what this causes is that the coercivity of the material is narrow. Probably this could be corrected by applying on the material later and annealing after additive manufacturing processing. The second problem is that the material is going to be, the powder is isotropic, but as well the magnet, the selective laser melting magnets are going to be as well isotropic. That means that the maximum remanence that we are going to have is about 0.5, 0.6 Tesla, which compared with an anisotropic sintered magnet, which has remanent of 1.3, 1.4 Tesla, is quite low. If the remanence is very low, you have to make bigger your motor, which was not possible in this case. So finally, we have not done a magnet by additive manufacturing in this project, and the magnets that have been used are anisotropic sintered magnet that have been bought. Regarding the soft magnetic material, we have considered three possibilities: supermalloy, permanduct, and an iron silicon alloy. Supermalloy is an alloy with very, very low coercivity. It's the material we have the highest permeability, but the point is that it has a saturation magnetization quite low. This is about 0.5 Tesla, which again means that you have to make bigger your design, the design of your motor. So it was discarded for this reason. Iron silicon is quite convenient because it's a cheap material. It has a saturation magnetization around 1.7 Tesla, which is high enough, and the coercivity is as well quite low. We did some builds with iron silicon, but the point is that this content of silicon is quite big. It reduced the ductility of the material, and during selective laser melting, there are quite significant thermal stresses. The material was brittle, and we could not avoid easily the formation of cracks during the deposition. So finally was discarded as well. And finally, the material with which we have worked is permandur. The main characteristic of permandur is that the saturation magnetization is very high, about 2.4 Tesla, which allow you to minimize, to reduce the size of the motor. So it was a good choice. The coercivity is as well a little bit high compared with the other materials, but this is especially important when the frequency of the operation of the motor is high. And I think this was not the case. So let's say the hysteresis loss was assumable in this project. So finally, the material of choice was permandur, and from now is going to explain Miren the work that we have been doing with this material.
Okay, so as Jose Manuel said, we choose finally this soft magnetic material that was permandur, and so with this material in Guille Mechanics, what they did was a process parameter optimization. This talk will be done later by Guille Mechanics, and once that we obtain the material with proper characteristics, what we did at SAID was a post-heat treatment optimization. The experimental work that we performed at SAID was related with the application of several heat treatments, and in order to choose the best one, what we were relating was which microstructure we were obtaining and how this microstructure was related with magnetic properties and mechanical properties. So talking about permandur material, the composition is iron cobalt and with 3% of vanadium. So we can follow the typical binary phase diagram that you can observe in the screen. The studied conditions were first as laser powder bed fusion or as SLM material, which is melt by laser and then rapidly cooled. And then the other conditions were after heat treatment, both after HIP, hot isostatic pressing, and also after conventional heat treatment. About the heat treatment, what I have to say is that all the heat treatments were done in this region, in the disorder alpha iron region, and then the difference were the different cooling rates and the different holding times. So starting from the base material that was the as AM or as laser powder bed fusion material, this material has very fine grains because this is related with the very fast cooling rate during the process. What we observe in X-ray diffraction experiment that I will show later is that this phase was reached in a disorder alpha phase, the one that is here with in this region. So this phase has good mechanical properties, but the problem is that it has very poor magnetic properties. And as this material is supposed to be to use for magnetic applications, we needed to change it. So for that, the heat treatments are very useful. The standard heat treatment considers to make a treatment at these temperatures with a holding time and then slowly cool. When this happens, the microstructure changes completely. And in this case, we can observe that the grains are very big. And although there are still a little bit of a small grain coming from the SLM material, most of the sample is based on these big grains that are related with the alpha prime order phase. So when changing from disorder to order, what we obtain here is that we have a very good magnetic properties, so where we were looking for, but on the contrary, we again lose the mechanical properties, and the material is very brittle and difficult to handle. Another thing that I wanted to say is that both in hot isostatic pressing and conventional heat treatment, if we do the same thermal cycle with a slow cooling, the obtaining microstructure and properties are the same. So from now on, we just were focused in the conventional heat treatments. Also because as the material from SLM was already quite dense, it was not the need of closing porosity by hot isostatic pressing. So the objective, as I say, was to try to have these magnetic properties, but not losing all the mechanical properties. So the study that we did was to try to change this cooling rate and see how the microstructure was developing and how this was helping to increase or reduce the properties. So there were three cooling rates: the slow one that we already saw with the big alpha prime grains, and then one intermediate that was called air cooling, and the fast water quench cooling rate. In the case of the water quench cooling rate, again, we observe that this, with a lot of small grains that are related with alpha alpha grains. And again, as in the material coming from the AM, we have good mechanical properties, but again, the magnetic properties were low. So it's clear that if we increase one property, the other one decrease. So finally, what we saw is that we have to achieve a compromise where we have an intermediate cooling rate that is giving us a microstructure with a mixed alpha prime phase and alpha phase. in addition, we did another study in parallel where we were changing the holding times. And in here, what we were wanted to obtain was if we were able to increase the size of the alpha grains and reduce the amount of grain boundaries, it was possible to also increase the magnetic properties without reducing the mechanical properties. Although this is not so high difference, it works, but it's still needed the intermediate cooling rate. So coming back to the microstructure, here we can observe X-ray diagram, in this case a magnification of a peak, where we can see that as a function of the heat treatment that this material has, the maximum of the peak is displaced to either one side or to the other. The ones in the left side are related with disorder alpha. So in this case, we have the ones that has been fast cooled, even as SLM or after heat treatment with the fast cooling. So this will be the phase that is giving the good mechanical properties, but bad magnetic properties. On the opposite side, we have the peak of the phases that has alpha prime, so good magnetic properties and bad mechanical. And in the middle, we can observe that there is another peak, and these are related with the materials that has been intermediated cooled. So they are supposed to have a mix of those two phases. So relating this microstructure with the magnetic properties, again, what we see is, as Jose Manuel said, the good soft magnetic properties are the ones in red. So they have very low coercivity, but high permeability and high magnetization saturation. And these were related with the ones slow cool. So heat treated and then slow cool. And the worst soft magnetic properties were for the AM microstructure, and in the middle, as we say, the ones that has been heat treated with different cooling rates. So conclusion, if we have a material that has been fast cooled from AM or after heat treatment, we are going to obtain a material that has a disordered alpha microstructure, which has very good mechanical properties, both in strength and in elongation. And as a sample, you can see here a fracture surface of very ductile material, but that has very poor soft magnetic properties. On the other side, we have, if we do a very slow cooling rate, we have a material that has ordered alpha prime microstructure with very good soft magnetic properties, but we lose completely the mechanical properties. So for Addimot project, what we needed and was finally the optimized conditions were the ones that were intermediately cooled, so with air cooling, where we obtained a mixture of microstructure and give us enough magnetic properties for the application and also enough mechanical properties for machining and also for the application itself. So, as conclusion, okay. As Jose Manuel said, the gas atomization process is a good alternative to manufacture soft magnetic and hard magnetic materials for additive manufacturing, because we have this feasibility of tuning the powders for the application. And also, it's important to know that there is a high interest in magnetic materials for AM, but that still in the literature, there are not a lot of successful attempts. So there is a need of researching these materials in AM. In our case, in Addimot project, we have been able to manufacture a soft magnetic material and then process by SLM or laser powder bed fusion with optimized parameters. And then thanks to the heat treatment optimization, we have been able to tune the microstructure of this material, achieving both magnetic and mechanical properties. So the final component was able to be applied with even structural properties. And thus we can say that this project has been successful in terms of this material optimization. And that is all from my side. Thank you. I don't know if there is any question. Okay.
Okay, so the next two speeches are given by Borja Prieto and Borja Lizarribar, who are members of the electrical machine design group here in Thate. They're going to talk about the possibilities of additive manufacturing for the electrical machines and the advantages and disadvantages, and also about topology optimization techniques, electromagnetic and mechanical optimization techniques. Okay, I give the floor to Borja.
Okay, hello, good morning. So as Miguel said, I'm going to present a brief review on the possibilities of employing additive manufacturing techniques applied to the design and manufacturing of electrical motors. First, by performing a brief review of the state of the art of additive manufacturing techniques, and then focusing on the results of Project Addimot. Okay, well, stating key actions performed and results obtained, and also moving into having a comparison between the additively manufactured motor that has been done in this project compared to a traditional solution for the same application, and stating the gains that have been obtained by shifting to additive manufacturing processes. And then I'll just end by stating some conclusions of the project regarding additive manufacturing of electrical motors and some future prospects regarding these techniques. So additive manufacturing is in fact a big concept that it's evolving itself. Okay, in here you have the main families of additive manufacturing techniques, okay, such as binder jetting, material jetting, direct energy deposition, so on. Each of those, in fact, well, those are families that in fact group more than one technique itself. Okay, here as an example in this picture, you can see a classification of the different additive manufacturing techniques, in which each of these colored boxes represents a technique on itself, and the white boxes just an example of an equipment manufacturer that is providing those techniques. Okay, for you to know, there are nowadays in the world more than 800 companies that are offering additive manufacturing equipment for polymers, metals, ceramics, biomedical materials, and so on. Okay, and as I say, technology is changing quite fast. So regarding additive manufacturing techniques, in the next slides, you have a global picture of the characteristics, materials, the typical applications that, well, for which these techniques are used. Most of the additive manufacturing techniques can be used for the manufacturing of metal, polymers, ceramics, sands, and many other kinds of material. In the majority of cases, well, the additive manufacturing, what involves is taking some base powder material and joining it by either using a binder or sintering those powders, or either fusing them by applying some energy in terms of laser, heat, pressure, electron flow, and so on. Okay. A different or a particular case that it's quite different, it's the cold spray technique. Okay, that instead of trying to bind those powders by applying pressure, or sorry, by applying energy into them, what it does is it just sprays the material at high speed onto a surface, and therefore obtaining a layer of material. So it's more of a coating process rather than a manufacturing process itself, but it's quite interesting, and it has been successfully applied to the manufacturing of permanent magnet materials. So regarding the additive manufacturing of electrical machines, the most common processes that are being investigated nowadays are binder jetting, material extrusion techniques such as fused deposit fused deposition modeling, or powder bed fusion techniques such as selective laser sintering or selective laser melting. So this table in here just outlines some of the main characteristics of the different additive manufacturing processes regarding attainable build size area, precision or resolution, whether support structures are required, whether the technique itself requires some post-processing after the part has been manufactured. So regarding the values on size and precision, the values are intended to be illustrative because, as I just said, technology is changing quite fast, and new developments are being made each day. Okay. So regarding project Addimot, the technique of selective laser melting was chosen for the manufacturing of the different motor parts because it's quite suitable in order to obtain dense metal parts with a very good precision. Okay. As my coworkers have stated, selecting the appropriate material and processing parameters is important, but selecting the adequate manufacturing technique is quite important as well. Okay, in this example in here, what we are seeing is a rotor, an electrical machine rotor concept manufactured by Said, using the laser metal deposition technique, which is a direct energy deposition technique. In this case, what you can see in the picture in the left is the processed part, okay, in which just the front surface has been machined. Whereas the picture in the left is the part after being additively manufactured and machined in order to meet the final geometry. Okay, so you can see that even if the part is dense and has no apparent porosity problems, and it has quite good mechanical properties in this case. Well, when being manufactured by laser metal deposition, the surface quality is quite poor, and in this case, quite the machining effort was required to have the final rotor geometry. Okay, so what I just want to stress in this case is that not only material properties and material processing is important, but also selecting the technique most adequate to the part you need to manufacture is important as well. Okay, in the case of selective laser melting using the Addimot project, it allows us to manufacture the parts with a very good precision and requiring almost no post-processing in terms of part machining afterwards. Okay. So moving on to the technology review of additive manufacturing applied to particular motor components, the following review intends to be just illustrative and present well, some ideas or some possibilities that the additive manufacturing of motor components allows. Okay, regarding hard magnetic materials, that it's magnets, this can be processed either by material extrusion techniques, binder jetting, powder bed fusion, direct energy deposition, and so on. Okay, in the examples, in the pictures you have in here, for instance, you have a magnet processed by fused deposition modeling. These ones in here have been manufactured by selective laser melting. And in this case, in here, in which this rotor component has a non-standard geometry, okay, this case in here has been manufactured by cold spraying the magnetic powder onto an aluminum substrate. Okay. So regarding additive manufacturing of magnets, quite promising results have been obtained in terms of material use and recyclability. Okay. Also, it's quite interesting that with additive manufacturing, the grain size can be quite precisely controlled, and this allows the material to have a good coercivity without having to rely heavily on rare earth materials such as dysprosium or terbium. There are also some promising results regarding having low losses in the magnet materials at high frequency due to having a reduced electrical conductivity. But in general terms, especially regarding the remanence, somewhat the coercivity levels are quite far from standard sintered magnets. Okay, for the moment, the properties of the magnets that have been produced by the additive manufacturing are more similar to those of bonded magnets produced currently with traditional techniques of injection or extrusion. Okay. The results are quite more interesting for the soft magnetic materials, as Miren has explained. In this case, material properties obtained, especially for powder bed fusion techniques, are quite good. Okay, several examples of silicon iron, cobalt iron, or nickel iron materials can be found in the relevant literature. What additive manufacturing allows, on the one hand, is to have quite complex 3D structures. Okay, it's the ones you can see in the pictures, and also it makes the production of some particular compositions maybe even easier than for traditional manufacturing. Okay, for instance, of high silicon or content iron alloys or iron cobalt alloys. Okay. So regarding the soft magnetic, well, the additive manufacturing of soft magnetic components, results for the moment are quite good. Quite the research efforts are being made nowadays in order to reduce the eddy current losses in the solid materials. Okay, as you know, any solid magnetic material that experiments a variable magnetic excitation will present some eddy current losses in the material. So efforts are being made in order for these materials to have a behavior similar to those that can be obtained by having the parts manufactured by traditional lamination. Moving on to coils and windings, this is also a quite interesting results are being obtained in terms of additive manufacturing, okay, especially regarding the addition of ceramic insulation onto the windings themselves, and also onto manufacturing freeform coils that have some enhanced features. In order for the coils to be better cooled. Okay, in these examples in here, what you can see are some coils manufactured by powder bed fusion techniques. Okay, that include some channels for a coolant flow to flow through them. Okay, also the geometry is optimized to have the minimum end winding possible, and also to have a reduced AC losses at high speed, at high frequencies, sorry. So the most interesting results regarding additive manufacturing of windings and coils are perhaps in this area, in having optimized coils for high power density motors that include the cooling and have reduced losses. Regarding insulators, additive manufacturing allows to quite easily process dense and porous ceramics, and according to some studies, they may help even reduce manufacturing time and cost. For instance, in this picture you have in here, this was a study made by a university in which an axial flux motor was totally additively manufactured. Okay, in the sense that the iron parts, the copper, and the ceramic and a ceramic insulator were all additively manufactured, and in this case, this allowed the machine to operate up to 300 degrees. Okay, although with a reduced efficiency due to the high current density obtained in the copper coils. Okay, so there are quite interesting prospects regarding the additive manufacturing of ceramic and insulator materials using additively manufacturing techniques, but quite the challenges remain regarding the resolution and the precision of the components that can be achieved. Okay, quite especially regarding the microporosity of these components, as this directly affects the thermal conductivity of the ceramic parts, and also the partial discharge behavior. If we move on to the manufacturing of the structural parts of electrical motors, this is also a quite interesting, some quite interesting prospects are available. The work that has been conducted has been primarily oriented to the reduction of the material use and the weight of the components. Okay, you can see in here examples of very lightweight rotor structures, in this case by having very thin walls, and in this case by having some lattice structure of the rotor components. Okay, the additive manufacturing of these structural parts can lead to significant gains in terms of a higher degree of integration of the motor components, and even to remove parts, as we will see regarding the project Addimot. And also another quite interesting application of this additive manufacturing is to have rotors of induction machines, solid rotors, made by, well, made by cold spray technique in which a copper layer is directly printed on the baseline rotor surface. Okay, therefore allowing very high speed for these motors. Regarding the additive manufacturing of cooling systems of electrical machines, also a lot of work has been conducted. Okay, it has been used for producing heat exchangers, heat guides, cooling channels, manifolds, cooling jackets, heat pipes. Okay, what additive manufacturing in these cases allows is to have quite complex parts, okay, with reduced weight, and also with enhanced features that allow well, the thermal transfer from the motor parts to the outer surfaces. Okay, so for instance, in this case, you can see in here some heat exchangers made by fuse deposition modeling. Okay, that on the one hand isolate the coils of a motor one from another and also allow the flow of a coolant through them. Okay. In the case of heat exchangers and cooling jackets, you can see also that quite complex patterns can be manufactured more easily than with traditional methods, and therefore, in order to obtain lightweight and very good heat transfer from the motor components to the outer surfaces. Okay, and lastly, some developments have been made regarding the additive manufacturing of sensors. But most of the work, from our understanding, is being applied to the manufacturing of biomedical sensors. Some examples of sensors that are of interest in the sector of electrical machines or magnetic components are the ones that you can see here, such as strain sensors, accelerometers, displacement sensors, force sensors, temperature sensors, and so on. So as you can see, what additive manufacturing mainly allows in these cases is to have very miniaturized sensors that are also flexible and that can be attached to almost any surface. The thing is that some challenge remains regarding sensor resolution and manufacturing speed. Okay. So now moving on to the additive manufacturing of the motor in the Addimot project. Well, the requirements of the applications have been already stated by Blaise, so I will not focus on that. In our case, based on the application and its requirements, the proposal of the project was to focus on the soft magnetic and the structural parts, even though, as Josema stated, some trials with permanent magnet powders were also made. In this case, it was reasoned that the additive manufacturing of coils was not interesting, being this a low power application, so a quite low speed one. So in this case, the number of turns of the coils were quite large, and there was no coolant flow available. So yeah, we decided that the additive manufacturing of coils made no sense, and we focused our efforts in the additive manufacturing of the structural and the magnetic parts. So from the requirements, a first step in the design of the electrical and the electromagnetic parts was to evaluate different motor topologies, such as double rotor ones, both traditional and holdback, axial flux machines, traditional radial flux ones, even some hybrid configurations radial and axial flux machines were preliminary evaluated. So based on the requirements and the different topologies, a trade-off analysis was made regarding torque capability for the maximum constraint of power that was stated by the specification, and also the weight of the materials. In this case, the best results were obtained for traditional radial flux configurations, okay, both inner rotor and outer rotor ones. In the case of Project Addimot, after this preliminary evaluation, it was decided to opt for a outer radial flux configuration, as it allowed an easier industrialization of the manufacturing of the coils. So this configuration was selected as the baseline for later refinements. So after that preliminary sizing exercise and some more refinements and optimization regarding both parametric optimization and topology optimization techniques, my colleague Borja Lizarribar will explain later. The final electromagnetic parts were defined. Okay, in this case, the stator part and the rotor part. What the additive manufacturing of these parts has allowed in the Addimot project have been these ones. Okay, on the one hand, to have a double behavior of the parts, in the sense that both the stator and the rotor have an electromagnetic and a mechanical function. Okay, therefore removing in between parts, okay, from these ones to the housing or to the shaft, and this has allowed us to reduce quite a lot the weight in designs, and also to have some interesting prospects in terms of reliability. Okay. Also, even if it's not presented in here, we have applied a special design to the electromagnetic parts in order to have a reduced cogging torque and torque ripple. This is not shown because it's patent pending from the consortium member side. And also in this case, maybe it's not quite prevalent, but what additive manufacturing has allowed is to place some holes through the parts in order to make an easier routing of the sensors. Okay, in this case of the thermal sensors located in the end windings of the most inaccessible part of the machine to the outer side of the machine without having to compromise the structural integrity of the motor by having this routing made through the metal parts. Okay. Regarding the mechanical design, also from some initial concepts, by applying topology optimization techniques, the final mechanical solution was implemented. Okay, in which you can see that the parts are quite optimized for the additive manufacturing. Okay, so very lightweight structures having complex geometries, quite difficult to obtain by traditional manufacturing methods. This has allowed to reduce the weight of the whole motor quite significantly, and also to have a simplified mechanical assembly. Also, an interesting point of having the motor components being manufactured by additive manufacturing is the better heat transfer from the motor coils, in this case the greatest heat source in this application, to the outer part of the machine. Finally, regarding the comparison of the additively manufactured Addimot motor concept versus a traditionally manufactured one, a traditional concept with iron silicon lamination for the stator and ferromagnetic stainless steel for the rotor was designed, but based on the same mechanical concept as you can see in here. Both designs were conceived to have the same power consumption and thermal behavior, as you can see in here. So what was obtained by additively manufacturing the advantages of additively manufacturing the Addimot motor concept compared to the traditional one in this case is 11% more length for the traditional concept and 23% more weight for the same thermal behavior and power consumption. In the case of cost, this was also analyzed based on a production of 48 units per year during 10 years, okay, with the manual manufacturing of the windings and the manual insertion of the magnets, and it was found that the cost of the two designs was almost the same, with just the traditionally manufactured motor being 2% cheaper than the additively manufactured one. So the sole advantage of a traditionally manufactured motor concept for the Addimot project in this case will be that the traditional concept will not have torque the rating with the speed, but this is not important for our application as the operation of the motor concept is almost quasi-static. Oh, sorry. So moving on to the considerations, what additive manufacturing has supposed in the Addimot project, it has been that, well, on the one hand, quite the efforts have been made to have a proper material characterization and a trade-off between the mechanical and the magnetic properties of the magnetic materials. Okay. Also, the considerations made regarding the selection of the adequate additive manufacturing technique. Regarding of the design of the motor parts, the additive manufacturing has allowed to design the parts almost freely, with no real restriction on the form or the geometry of the parts, beyond some little considerations regarding the print direction, the mass or the shape of the parts, in order to avoid overheating during the additive manufacturing that will lead to deformation, and also the tolerances and surpluses that have been added in order to afterwards have the final geometry after machining the critical surfaces. So the benefits in this case of using additive manufacturing have been reducing the weight of the volume for the same performance and cost compared to a traditionally manufactured option, to have a quite simplified mechanical arrangement, and also to add some special features in order to optimize the cogging torque and torque ripple behavior. Regarding future prospects of additive manufacturing of electrical machines, it must be said that even if additive manufacturing is fastly evolving, the manufacturing of electrical machines via additively manufacturing is quite in its early phases of development, being very little examples of machines being fully manufactured in additive terms. Okay. But there are quite some promising perspectives in terms of having complex 3D multifunctional parts, okay, that have electromagnetic, thermal, and structural behavior, okay, such as in the case of the Addimot project. Also, in terms of having two material composition properties by controlling the grain size and grain orientation, and therefore have anisotropic properties. to have freeform coils with very high field factors, reduced windings, and direct cooling for high power density applications. To have a direct deposition of high temperature ceramic insulators on e-motor parts, and also to use lightweight topology optimized structural and cooling systems for increased power density and material savings and very good cooling of the motor part. This has been all. Thank you very much for your attention. And if you have any question, just feel free to ask.
We have questions from people who's attending online regarding surface finishing and the post-processing of the manufacturing of the motor. But I think we must wait for the presentation of later after the break. They are going to focus on the manufacturing processes later on.
Okay. Thank you.
Okay, so I am Borja Alzarribar, PhD student at FATE, and I'm going to present the electromagnetic and mechanical topology optimization of electric motors. So here's the index that I'm going to follow through the presentation, and I will start with a brief introduction about what is optimization and how is it applied to electric motors. So optimization is a common problem in engineering which tries to maximize or minimize an objective function. So in electric motors, this objective function is normally torque, power, efficiency, and it can be also to minimize weight. So how is this applied to electric motors? We can see here an image of a double rotor motor in which we have parameterized all the main parameters of the motors that can be, for example, the width of the magnets, the yoke of the rotor, and the height of the magnets. So in parametric optimization for motors, we are changing the values of these parameters to find the best combination of them to achieve the better performance. So to optimize the torque or the efficiency and so on. So, sorry. Okay, thank you. So this optimization method is widely used because of its performance and because it's very fast. It's not very time consuming. However, this optimization method is constrained to the initial topology that we are setting. So to overcome this drawback, topology optimization is becoming to be studied in electrical motors. So what is topology optimization? So topology optimization tries to optimize the topology of a motor to achieve the better performance of it. So here we can see how is it done. We have to discretize the design domain of an electric motor, and it's in different cells. Here we have triangular cells, and each cell will have a cell density which will vary between 1 and 0, and being 1, the material that is being studied, in this case electrical steel, and 0, void or air. So topology optimization tries to do the combination of these cell densities to find to minimize the objective function that is normally torque related. Okay, so once we have presented topology optimization, I'm going to start with the main techniques that are used nowadays in topology optimization. So the first one is the level set method. In this method, the main characteristic is that in each iteration, it changes the mesh of the topology. So you can reach the final result with a very good border between air and iron. The density here is only 1 or 0, so there are not any intermediate materials. However, the main drawback of this method is that by itself is not capable of making void regions, air regions, and you have to add a bubble like in here, like a initial air bubbles to achieve a good final solution. Okay, next technique is the on-off method. The on-off method is the most easy one, as it discretizes, as we have said, the design domain in cells, and it puts this cell on material or inert. So it tries to maximize the objective function, just putting these cells to material or air. We can see an example here in green, in which in the first iteration we have all the cells in material, and in the last iteration we have optimized to reduce the weight, but not compromising the structural part. So how is it done to change the cells from iron to air? Is done by calculating the influence of each cell in the objective function that we want to calculate. So for this, we use the topological derivative. So to illustrate what is this, I have this image, this blue image, in which we can see the influence of each cell of a synchronous reluctance motor in the torque. So we can see that there is a zone in which the influence is higher than, for example, in the lower zone of the rotor of a synchronous reluctance motor. So to calculate the topological derivative, we have the finite difference or the adjoint variable, and the adjoint variable method is much faster than the other one. Okay. Okay, so also a good thing about the on-off method is that it can be combined with the now famous genetic algorithms. But however, because of the very time-consuming genetic algorithms, they are usually combined with normalized Gaussian networks, which is a method for reducing the time of simulation of the genetic algorithms. So for using that, we have to discretize the design domain in different Gaussians, and each Gaussian will have a diameter. So it's very important to define well the number of Gaussians and the diameter of them to achieve an optimized final solution. So here we have an example that we have done. It's a on-off method with Gaussian networks in which we have 4 materials. The pink one is the permanent magnet magnetized in the radial direction, so in this direction. The green one is the permanent magnet magnetized in the tangential direction. The dark blue is the electrical steel, and the light blue is the air. So we have an optimized machine for these 4 materials. Sorry for that. Wait. Okay, so here we have the SID method now. The main characteristic of the SID method is that we have densities between 1 and 0, so we can have intermediate densities that are not feasible in reality, but we can simulate them. For example, here we have the permeability of the material, which is dependent on the density of the material. I would like to show a video about this. Sorry. Okay, so here, no. Eso es. El siguiente. Esa es la diapositiva. La siguiente. Siguiente. Ok. Dale una vez más. Okay, here we can see a video in which the SIM method is working. So at each iteration, we can see how the algorithm converts material to void. So we have a weight optimized structure for a surface permanent magnet. It can also be optimized for multi-material, as we can see here, for a mechanic optimization. Okay, so this final optimization is a shaped optimization. It's not a topology optimization method, but as it is commercially available in Altair and some mechanics components, I like to just show it. I will talk about later. Okay, so now topology optimization methods applied to electromagnetics. We can see here that we have some examples, and it is applied only electromagnetically. And we can see here, for example, that we have this blue machine in which is taken right from the topology optimization method, and we can see that the borders between air and iron are very irregular. So it is clear that it is in need of post-processing after all, so we can have the kind of structures that we have here. So another very important aspect about electric motors is the mechanical aspect. Here we have an image of a Porsche prototype, a axle. So here we can see how they have topology optimized the housing. And it is clear here that topology optimization goes hand in hand with additive manufacturing, because as we can see here, this part could not be easily manufactured with traditional manufacturing. So I just wanted to point it out that additive manufacturing and topology optimization, as Borja has said, goes hand in hand. And thermal optimization, topology optimization, the thermal topology optimization for electric machines has not been studied, but it's a very interesting part. And we can see here for another application that from a classical pin structure to a topology optimized structure, we can have a reduction in temperatures of 17% in a heating test. So these optimization methods could be applied to housing to achieve better performances of the motor. So finally, the multi-physics optimization. Here we have two examples of electromagnetic and structural combination of topology optimization, and here the objective function is a combination of the two aspects, and here it's electromagnetically topology optimized, but the mechanical part is just a check. Okay. So traditionally in electric motors, the SIM method has been applied. However, as I have told you, with the Gaussian network, on-off methods has been started to be applied. And here we have some commercial software of Altair, as I have told, that is surface optimization. And we can see there that how it optimized, and JMAC that has introduced the electromagnetic topology optimization. So now I'd like to introduce a case study about a surface permanent magnet motor, which is going to be optimized with SIMP, on-off, and saturation methods, and they are going to be compared. So saturation method is in an in-house developed algorithm, which is an on-off method with a petit mesh, and it simultaneously optimizes the rotor and the stator, and also it does a magnetostructural optimization. So here we have the final shapes we obtain. We can see that in saturation method, the area loss of the rotor is not as high as in the other two methods. However, we have also taken some material from the stator, and the computation time of the saturation method is much lower than the SIM method and the on-off. So it's crucial to know which method is good for each case. And now I'm going to Okay, so now I'm going to present how topology optimization has been used in Addimot project. Due to the small jokes of the electromagnetic model, electromagnetic topology optimization has not been done. But for the blue path here, which is the stator, has been used as mechanical topology optimization, which is done in Permendur, and its actual mass is 1.61 kilograms. So the force considered are the ones of the normal magnetic force and the tangential magnetic force, which is the torque. The red zones are the ones that are excluded from the topology optimization, and the mass should be less than 75%. Okay, and here we have the final model of the topology optimization, and as we can see, as we have seen in the other models, the rough surface made to have a final smooth part, which is this one, and we can see how successful has been here to topology optimize the part, as we have lost 50% of mass from the first part. So finally, an overview of the topology optimization, if I can. Okay. Topology optimization is a growing optimization method which is able to maximize certain parameters of the motor and save material while manufacturing. However, as we have seen, topology optimization, the results of topology optimization are not easily manufacturable with traditional manufacturing. So it goes hand in hand with the additive manufacturing of electrical machines. So lastly, a last comment about electromagnetic topology optimization is that it's not as developed as mechanical one, but it has been started to be studied as in Altair and some commercial software that I have shown. So thank you very much. Hope you have enjoyed the presentation. And if you have any question.
I have a question from the audience online. You have said you have oriented your techniques with topology optimization techniques mainly on the removal of material.
Yep.
But it is possible to also add material in the process so that you will ensure that the direction of your convergence is right.
Yeah. For example, in the same method, it can also add or remove material in the same way. In on-off, there are two kind of methods. The bidirectional that does this, that if it has taken material from a zone, it can put it again. So it's possible to do that. Yeah. Okay. Thank you very much.
Okay, thank you very much, Borja. So it's coffee time. Okay, so we have a break now of 30 minutes to have a coffee, and we come back at 10 to 12. Okay, so thank you. Okay, so let's continue with the program. Now Sergio Montes from Aguile is going to explain us the manufacturing process. Probably there will be questions about the finishing and tolerances and so on. So please, Sergio.
Yes, okay, thank you. Okay, well, hello, good morning. Thank you for being here with us today. My name is Sergio Montes. I'm a research and development engineer in Aguile, and I'm responsible for the additive manufacturing of the Addimot project. So before starting this presentation, talking about selective laser melting of magnetic, structural and magnetic components, I would like to start with a brief introduction explaining how additive manufacturing, in this case, selective laser melting technology, also called powered bed fusion, plays the role of a game changer, not only in the field of aeronautics, but in any other sectors. Starting from the design, we now see very much geometries that have been designed for topological optimization or generative designs. When speaking about additive manufacturing itself, it's time to leave behind the idea of materials difficult to machine and start talking about capabilities of manufacturing different materials with this technology. When speaking about post-processing and related to the questions, we are now seeing many different technologies that weren't used as, for example, chemical pickling, sandblasting, abrasive flow machining for inner holes, and any other technologies such as electropolishing. And also, of course, laboratory and testing, such important in the field of aeronautics. So the way we position ourselves in Aguile with additive manufacturing is working hand in hand with our clients in order to make the most of additive manufacturing and designing many different complex geometries. When speaking about materials we've worked with aluminum alloys, titanium alloys, nickel-based alloys, such as Inconel 718, and we've got some future research trends related with material copper. Talking about post-processing, we've got more than 30 years of experience on machining microfused parts, and NADCAP certification for non-conventional machining and chemical milling. And we've got an on-site laboratory for metallographic test, very well-known process in aeronautics and also to check microstructure of additive manufacturing, and also NADCAP certification for non-destructive testing. So in order to put into context what the project Addimot we've developed along with it, we're starting with the design and simulation of this motor in order of the aspects topic leader Safran has explained, and along with that, doing in parallel the material characterization of this. Once we've developed good parameters development for additive manufacturing by powered bed fusion technology, we started with the manufacturing of the prototypes and also the quality control that I've explained. So it's such an important in the field of aeronautics. So for those who are not very familiar with this technology, powered bed fusion laser-based technology, as you can see on the picture on a build chamber, a laser source is in charge of melting powder, which is located on the bottom side of the platform. So in an inert atmosphere with an argon flow in this case. So apparently the technology is very simple. A doser will dose a certain amount of powder on the back of the platform, and a wiper is in charge of spreading this powder on the bed. After this, the laser is in charge of describing different trajectories in order to manufacture the sample part. The platform will descend the certain amount of height with the layer thickness we will be working with. And this process will be repeated once again until you obtain built part with all covered by unmelted powder. This unmelted powder could be shipped and reused in this technology. So in order to manufacture these parts, as our colleagues from SAID mentioned, of working with soft magnetic materials, we've used a solid state high terbium laser fiber with 1070 nanometers of wavelength and a spot size of 75 microns. So in order to understand how we've developed the different parameters in order to check the laser melting parameters of this technology, I'd like to briefly explain how the laser works, if it works. So as you can see, the laser will develop different scanning strategies in which the laser is in charge of exposing different spots. If you check at this picture, you can see a Gaussian distribution of energy density in the melting of the powder. So by changing many different parameters, we will be working with different energy density levels in the melting of the powder. So the main parameters we've checked in order to develop this laser scanning parameters has been the hatch distance, which is the distance between the scanning lines, the laser powder, and the point distance and the exposure time between this exposure that determine the scanning speed of the laser. In order to put an order of magnitude, when we between the different exposures, we are talking of microns and microseconds. So once you've understand more or less how this technology works, it's time to develop laser scanning parameters for this technology with a design of experiments. As you can see, there has been some test tubes manufactured, some vertical and diagonally. After this, we've CT scanned them in order to check for cracks and micro cracks. And after that, we've done a metallographic test in order to check the microstructure and possibilities of porous sections. So once we've done all this with image treatment, we are able to quantify the density and the porosity of these test tubes. So the first soft magnetic materials we start working with, as our colleagues from THEID has explained, has been the iron silicon, a very difficult material to additive machine manufacture. 4 different iterations needed to be done in order to avoid cracks and micro cracks of these test tubes. In order to understand how this technology works, as you can see, when using high density energy levels, you've got not very porous sections, but as you can see, cracks and micro cracks have appeared on the CT scan and the metallographic test. When using very low energy density levels, we will get no cracks, no micro cracks, but very porous stones not suitable for this application. So as you can see, our design of experiments have been checked all through the on the diagram, as you can see, on powder and different scanner speeds. Until the 3rd iteration, we weren't able to avoid these cracks. And on the last iteration, we were able to do it, but we had 1.3 porosity levels on our last attempt. So we concluded that this wasn't suitable for the application. So the next material we worked with was with permandu, that only 2 iterations needed to be done. In the first one, we already checked that there were no cracks on micro cracks, but we had some high porosity in the borders, so we had to also do a design of experiments in order to improve these border parameters. And the second iteration was done getting density levels higher than 99%. So as you can see, these were the energy density levels chosen for the permandur, and clearly, as it was shown before, when using low energy density levels, well, you get lack of fusion. And sometimes when using high energy density levels, you get these round pores. That means that evaporation have occurred during the laser melting. So once we've finished with the parameter developments and the manufacturing study, it's time to check the magnetical and mechanical requirements along with AID after the heat treatment. After that, before starting with the manufacturing of the prototypes, some test tubes in order to check mechanical and magnetical properties, and some test tubes in order to check manufacturing cutting speeds. So you can see some grooves, some holes, some threads in order to get similar to the final design. So here you can see the manufacturing batch of soft magnetic materials of Permendur. In this case, as you can check, both two rotor and stator have been manufactured in the same batch. And as you can see, some control height porosity bars that have been checked in CT scan. After that, the heat treatment, Miden has explained. After that, it's time to remove the build parts and supports from the platform. And curiosity of this material when applying this heat treatment is that it becomes a brittle. That's why we've decided to take off these extra materials using grinding and also drilling. And afterwards, the dimensional control test and CT scan in order to check that there's no cracks or micro cracks in the manufacturing of these components. And as you can see also the casing, which has been topological optimized. After that, heat treatment of a stress relief and the machining as mentioned. Well, once we've got the active parts of the motor and the casing and also the lid, well, it's time to assemble the component with the help of Lancor, in this case, a company specialized in the manufacturing and assembling of electric motors. And after that, it's time to test our prototypes that I think Miguel will explain you afterwards. So thank you for your attention. If you got any questions or any online questions, I'll be pleased to answer. Questions about surface finishing and post-processing parts. And yes, in this case, we've used grinding and machining in order. I know everyone here probably already understands that additive manufacturing has its limitations on surface roughness. So when designing these components, you need to give that extra material to your additive manufacturing prototype. And after that, well, applying traditional methods, in this case, grinding or machining. We have an additional question regarding the high cooling rates coming from the SL technology. Would that be better to use EPL? Well, actually, that's a very interesting point. Yes, probably yes. Oh, but on an hypothetical point of view, afterwards you need to check that everything is according to specs, as we have checked already with selective laser melting.
Okay, so now it's my turn. This is the final presentation of the presentation round in this workshop. Later, after that presentation, we will visit the optimization plant of SAIT. Okay. It will be a very short presentation. It will be very short. It's just the final results of the tests. Okay, as it is normal in this kind of projects, due to the lack of time, the test campaign wasn't as good. Okay, or as as intensive as we would like to. Okay. But we managed to test the motors so that the functional requirements were verified. Yeah, here we can see the test bench, very simple. I have the motor coupled with an elastic coupling to a torque meter, okay, and a crank fully monitorized with torque meter for the torque, but also voltage and current sensors and temperature sensors, of course, for the temperature testing. Okay, so we proceed with the yeah, we proceed with the test, and of course the first problems arose. Okay, normal. Okay, the first two prototypes, everything was okay. The third prototype have some problems with the windings. Okay, probably because the requirements were not very good. And okay, we tested the induced voltages of every prototype. Let's say, yeah. No, I'm sorry. We're having problems with the device. Okay. Then we proceed to normal tests, resistance measurements. Okay, quite good estimated by the design. It's only a 5.8% of underestimation of the resistance values of every phase. There's a 6-phase motor. Then more importantly, yeah, the magnet flux linkage measurement. Okay, the magnet flux linkage is key for the behavior of the motor, and the estimation, the predicted value was 18.95 milliweber. Okay, the measured values were very close to it. Practically the same, 1.5% overestimation of the magnetic flux linkage. So with this measurement, we were more relaxed because the machine was quite okay. Please. It doesn't work. Okay. Thank you. A torque, a very simple torque versus current test. Okay. Unfortunately, we haven't had the converter to drive properly the motor, so we proceed with a DC current test and quasi-statically move the rotor so that we proceed to measure the torque versus angle of the motor, and we measure the main Newton meter value for the 3 prototypes of 8.06 Newton meter for the given current, which is a very good result comparing with the estimation. Okay, it's almost no discrepancy in this. So here the objective of the standstill torque was achieved. Then we proceed to the heating test at standstill also, providing maximum current for the 8 Newton meter during 2 minutes, which was the requirement from the topic manager. And we verified that the temperatures were under the limits of the insulation system. In fact, it's quite a, let's say, cold motor, which is very good for the application. Yeah, and finally, the DC power consumption. The DC power consumption should be under 150 watts, and we measured this power consumption. At the end of the heating test, because it's the worst case, is where the resistance of the phases are hotter, or the windings are hotter, the resistance is higher. And so the worst case is this point, and we were under the 150 watts of the requirement. And finally, the weight. Okay, the weight, the requirement of weight was 3 kilograms. Okay, we're slightly above 150 grams above of the motor. It is very easy to reduce this weight, but as we have designed it, these prototypes was not possible in this project, but for a further improvement of the motor is quite easy. The thing is that we segmented the magnets in an 11 millimeter magnet. Okay, so we could reduce, for example, from 55 millimeter to 44 millimeter the length of the motor, the active length. Okay, but from 44 to 33 millimeter, which is a great reduction of weight, we couldn't do it because the DC consumption was above 150 watts. But for example, for a second round or second design, it would be very easy to use block magnets, not segmented, and to reduce, for example, 3-4 millimeter the length. We will be well under the 150 watts of consumption, and this 150 grams in excess that we have, we could reduce it. Okay. We also performed the safety analysis for the system. It's quite, this is 22.5 failures per million hours is quite good. This is not exactly the aim of the project, but it results that the actuator works with very low temperatures, and it is also low voltage motor, so the reliability of this kind of actuator is quite good. And finally, to sum up, I would like, to stress out that our intention is to do further testing of this motor with environmental conditions, like cold conditions and also hot conditions, the torque curves versus current, but also drive friction and cogging torque that was not possible due to time reasons, time constraints. We are in collaboration with Safran to do these tests out of the project, so it's not easy to find the time and the resources, but our intention is to do further testing to see which are the limits of this actuator. In fact, it is very new technology for electric motor. It is new manufacturing techniques. It is new materials. So this testing, I think, would be very interesting for us. And finally, and to close this session, I would like to talk about some lessons learned as a brief summary of everything that we have here today. Yeah, the first one is quite obvious, is that the additive manufacture is valid for magnetic and structural components for electric motors, with some constraints, of course. Okay. The magnetic alloys processed by gas atomization present very good magnetic properties and are very suitable for additive manufacturing, of course, with a detailed design, a tailored design of the powder production. The selective laser melting is very adequate for complex magnetic parts manufacturing. Okay, we have, let's say, verified or demonstrated that it is quite competitive in manufacturability, cost, process, and time, final tolerances, and surface finishing, and also design flexibility. Very important. The design flexibility of SLM is I think, best in class among all the additive manufacturing techniques that we have studied. And of course, the proper SLM process parameters and heat treatment selection leads to a good balance for mechanical and magnetic properties. This point is very, very important because we have do intensive work in this, lots of months, trying different heat treatments and also SLM process parameters to achieve a good trade-off between magnetic and mechanical properties. There was a time that we thought that we couldn't do it, but we managed with it, and it is very, very, very important to have good properties for the electric motor components. Regarding the electromagnetic and mechanical topology optimization, this techniques enables new performance for electric motors, not only in terms of weight, but also in Coggin-Torque reduction, ripple reduction, increasing filling factors, for example. I think it has been said here, but there's a, let's say, a new geometry enabled by the additive manufacturing introduced in this electric motor that is patent pending regarding Coggin-Torque reduction and ripple torque reduction. It is true that, for example, for parts, for stators, let's say, or parts subjected to AC magnetic flux, for example, high-speed motors or medium-speed motors, probably this, or the, let's say, the process that we follow here in Addimot is not adequate because iron losses are very, very high. Okay, so it's suitable for quasi-static motors as the one of active inceptors. But for example, for other parts, as rotors, for example, in synchronous motors, and of course structural parts are very, very good in any application. And another lesson learned is that it's very adequate to see the electric motor components produced by additive manufacturing with both magnetic and structural functions. Okay, because you reduce the number of parts of the motor. This motor is made of only 4 parts. Okay, it's the stator and it's the rotor together with the shaft, so it's only 1 part. The casing and the cap, and just the cap is only 4. This increases reliability. This avoids problem regarding joints. This avoids problem regarding different thermal expansion coefficients of materials, and I think it's a very, very good idea for further investigation of this kind of motors. And that's all from my side. I don't know if there's any question or general comment. Yeah, it is for second. This is previous session. Okay. So I think we can close the session. Thank you very much for the online audience. Now people here in State, we're going to visit the atomization plant, to see the additive manufacturing facilities. Thank you very much. And I think we can close the session here.